Is it record? Yes, it's recording. So so far, just checking with you guys if you have any questions on advanced digital systems design. Noted that I think you guys are a bit different. I think Iz has finished VLSI. I'm not sure if Alvin you finished VLSI, but you mentioned you submitted the DSD for
I've submitted the VLSI first assignment, I think, 2 weeks ago.
2 weeks ago. Okay, wonderful. I haven't checked yet. I'll go and check
Yeah.
it lah.
I think I already completed the second one as well. I haven't uploaded it yet.
Wonderful, wonderful. So
Yeah. Sorry, the
VLS
second and the third one as well.
the
Yeah.
second one. Okay, wonderful, wonderful. So you're a little bit further along lah.
Yeah.
Is will catch up at his pace. Uh, Tomorrow evening, if you guys are okay with 8:30, we will have the VLSI Q&A that time lah. Mm.
Oh, okay.
Today is focusing on digital systems design.
Mhm.
Anything you'd like to raise, any questions? You want me to repeat a certain part? You want me to talk a little, clarify any concepts? That'll be good lah. Then after that, I have maybe half an hour, 45 minutes of material to present on static timing analysis lah. And even tomorrow, VLSI, after the Q&A, I have about half an hour, 45 minutes to present lah. Okay, so let's just see what questions you guys have and can answer that first.
Mhm. Is there any materials or anything which we can use to brush up our very low skills?
Verilog skills. Got the textbook that provided. Let me just walk you through that. Let me share my screen. The textbook that's provided by Chu. That one actually has a nice, very steady introduction to the various ways of designing lah. Okay, let's log in quickly. So ADSD. So you should really make use of that because this is like full textbook. So sorry, let's go back here. If ADSD, you look, there are actually 3 textbook I provide you lah. So William Daly, the digital systems design one. This one is also a good example. It's got Verilog in it lah. But this one actually is like he has a full textbook on this, published by Cambridge University Press lah. So okay, let it load first. I think it's a bit big. It's published by Cambridge Digital University Press. So the book is a bit expensive lah, but this one is like a copy that was available freely lah for his Stanford class. So it doesn't have all the chapters, but if okay, I don't know why it's not showing. Let me download it and then maybe we can see. Save link as. Okay. So if you check the okay, sorry, I didn't share the. Okay, let me go through the Chu book first. Then I mentioned the Chu book is specifically Verilog and digital design. William Daly one is a little bit part undergraduate and then a little bit more advanced on graduate lah. But the Chu book is a bit more focused lah. So if you go to basic digital circuits development lah. So this is the talk about it, RTL for combinational circuit lah. So here you have the coding guidelines. So here if statement. So here is all he's going through in gory detail, all the syntax and all that lah, routing structure. So it shows you this circuit, how do you actually code it up, all that. So this is more like a revision of the compressed version I've given you in the first tutorial that we talked about. Here's a compressed statement. So you have the if statement, else statement, routing, then coding guidelines. This is like best practices lah, how you write Verilog in this textbook lah, Verilog FYI. And then the best is you actually got the design examples lah. 310, it's got like the 7-segment LED decoder. This is exactly the full code. How do you do that 7-segment display? Then you got a sine magnitude adder. So these are different combinational block examples lah. Okay. So what you can do is maybe for practice, if you want, either you can either go through this or you can challenge yourself. You understand what it's doing, then you do your design, and you compare with the example code lah. So there are so many examples here lah. Like okay, and then suggested experiments. You see there's multifunction barrel shifter, parameterized barrel shifter, dual priority encoder, BCD incrementer. All these circuits you can just design in Verilog to your heart's content lah. So this book has plenty of example. So chapter 3 is just the combinational logic. Chapter 4 is sequential circuit lah. Sequential circuit. So here you see the example of coding with flip-flops, okay, the always block. Again, we've covered these, but because of the time constraint, I had to cover it very quickly. I just gave you the gist lah. But you can revisit that video, but you can also read through this in a very systematic way lah, because this book is really complete lah. Like it just walks you through with design example after design example lah. Just from the very basic flip-flops, registers, then it gives you a shift register design, universal shift register, your binary counter, okay, your mod M, modulus M counter, then it shows you how to write the test bench, then it's got the case study, your LED multiplexing circuit. It's got a lot of case studies, and then got got problem questions. That's the experiments lah. Then got a stopwatch example. You can go through this. It's all full code. It's describing all of this with full code lah. Clock tree. Then again the suggested experiments. How do you get a programmable square wave generator? So these are actually real circuits. You can go ahead and practice designing these circuits. But I'm not requiring it from you for your assignment lah. This is more of like your self-paced learning lah. So chapter 3 and 4 is good basics. Chapter 5, finite state machine lah. Finite state machine basically is a millimole machine again. So you see your state transition diagrams, your algorithmic state machines that Mr. Low had already covered. So just again examples of, they walk through it, they show you how the code is written. But as I mentioned, basically you'll find everything is just always block, case statement. I showed you the coding styles in brief really lah, but perhaps that wasn't because the nature of my tutorial was I just give you the gist quickly lah. But you also, this resource provided to you, you also can go step by step with all the work examples here lah. You will take some of your time, but if you walk through this in a systematic fashion, you will really be able to master this lah. It's plenty of examples here lah. And again, above are all the work problems, the work designs. Here are all the designs that you can test your skills to design. And again, if any of these you've tried, you're stuck in like not really sure how to complete the design, you can mention to me and we can have a tutorial session where I'll walk through the design with you lah. Okay, and as a FSMD is like a little bit more detail lah. What does D stand for? A data path. Yes, this is a data path finite state machine lah. This is going back to, again, as it was mentioned in the DST, one of the design principles is you have to separate the control and the data path lah. And this is actually showing you how the data path, how do you think about it in terms of a state machine or an algorithmic state machine. So if you see this if-else decision, this is ASM, algorithmic state machine. Without the if-else, that's a regular finite state machine. So chapter 3 to chapter 6, all the basic. Okay. So selectors topics is more of like chapter 8, this is more of like best practices lah. You want to go into more detail. Chapter 7 is talking about a FIFO buffer, memory controller. Is linked a little bit to what the project I gave you, but the assignment project that I'm giving you, that I'm building up, is more detailed than this one lah. This one is just doing a basic SRAM type of access, the decoder, but these one are not clock circuits. So they are just doing RAM to access it with the row combinational logic lah. But and then the FIFO buffer, this is also a very good part because this is what we'll be coupling with instructions lah. Later in the course, is almost soon already, we'll actually give you an example of this. But these are the basic element lah. So what is different is in the assignment I'm giving you, we're actually building an entire SDRAM circuit lah. And the entire SDRAM circuit, I just share with you. If you look at this, this is the entire block diagram that I'm going to show you. Okay, so just now the textbook is only covering row decoder, row buffer, column selector. So maybe it's focusing more on the row decoder. How do you select particular array of the SRAM? Then the SRAM array, that is more like an analog circuit. I've given you the behavioral model in Verilog already under, I think, assignment 1. Okay, the SDRAM basically is adding the base register and then a stride register. That is how many rows from the row buffer you want to access, sequentially lah. And then there's an address counter, and then a column selection multiplexer lah. That this part of the circuit is going to be that's the assignment 3 lah. That is the SDRAM addition lah. Okay, because SRAM is not clocked. SRAM is just is a address in, you read and write signal. That's what you get. Okay, but SDRAMs static. Sorry, it's not SRAM, it's DRAM lah. DRAM circuit is that. SDRAM is synchronous DRAM. So synchronous means it's clock. So it means that these two features lah. That is this counter and base register that you can address consecutive columns.
Is this part of the bit slicing one? The under module 3, the assignment you're talking about? Hello? Hello? Hello?
Yeah, I can hear you, your voice, Alvin.
Yeah, I think I can't hear his voice. I can't hear. Hello, doctor? Can't hear you. Hello? Can you send a message? I think it's frozen.
Yeah. The line.
Wait, let me send a message. Hello? Hello?
Guys, hi guys. I don't know what happened just now. I just got booted out lah. Okay, let me get back lah. I was talking to you about the SDRAM, and what was I doing? Yes, I was going to tell you that this is your, sorry, this is not SRAM lah. This is the DRAM, dynamic RAM array. SRAM is more like caches lah. It's a 6 transistor cell, where DRAM is a 1 capacitor cell. Okay, so assignment 3 is basically looking at the base register, stride register, address counter, and column selection multiplexer lah, that additional circuit. So this DRAM array is made like a 3-dimensional box, because what you have in assignment 1 is just a 2-dimensional box. That means you got multiple rows and multiple column. Each row and column gives you 1 bit. So when you grow it in depth here, okay, that is where you get your 8 bits. This is where you have, let's say, like a X8 or X4 lah. X4 means 4 bits, X8 means 8 bits lah. Because if you look at DDR RAM specification lah for your DDR4, what you always find that for that particular memory module, there's an X4, X8 existing. That just means that how many in the DRAM array here lah. So that is where we have the bit slicing concept, where we actually have the same row decoder, and the same row decoder is going to address 8 different DRAMs array. Okay, the rows of 8 different DRAMs, because you want to get 8 bits, right? So one array gives you 1 bit. Every time you have one row, you get one whole row of bits. And then the column select marks, there's going to be 8 of them, right? If it's a times 8, right? And the same signal for the column select will go to all 8. Okay, so yeah, and then the row buffer, there's going to be 8 of them as well in depth. Okay, so that we in assignment 1, you only were looking at the row decoder, the address counter and all that, but for 1 bit. But assignment 3, I asked you to fill it out into the full 8 bit. Then you have to actually repeat into, I think, 8 bits and all that, and you have to just route the appropriate signals. Okay. What is remaining basically is a few things. One is when you are requesting the DRAM access, right? there is going to be a certain amount of time where, you know, like the row access is going to take certain time, then the column access is going to take another certain time and all that, and they all don't happen in the same clock. So there has to be some kind of control here that will basically wait, you know, to place the address, then you'll wait, you will not update the address. So there's some kind of control logic, and that's the state machine that is assignment, I think assignment 2, or I think it's assignment 2 that you are supposed to do. So that is that control logic that will just wait and all that kind of thing. But you realize that that control logic that is allowing you to wait to do the row address, column address, if there's another memory request that comes, because you cannot control when the memory request will come, right? You cannot tell the processor, you know, don't tell me, right? I mean, you can, and that's the signal, that's the, going back, the signal is like, stop lah, stop, like, you can do that, but I'm going to actually explain why we have this FIFO and all that later. But I'm just saying that if you don't have any other like intelligence on this front part, the processor is just going to keep giving you memory requests, right? Read and write requests, and you also won't be able to stop the processor, right? And if you are still processing one request, the control logic has to be able to tell the processor, whoa, 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 stop. Okay, so that's where we start looking at the control process, where what we do is we have a FIFO buffer, first in, first out. Okay, and the FIFO buffer, the processor will just basically keep stuffing things into the FIFO buffer until the FIFO buffer is full. Okay, and the nice thing about that is because what you're doing is basically you're putting the memory request into a queue. So a FIFO buffer, another name is queue, right? Because it's first in, first out. Everything is going into a queue. People going in one. So the first one to go in will be processed first. So a FIFO buffer is a nice way for you to balance out, like, so you don't actually have to put too much control on when people send you information or requests. Okay, so that's why we have the FIFO buffer. That's supposed to be assignment 4, but we haven't actually put up the FIFO code for you. But if you like, you can actually just take the FIFO code directly from here. This circular queue, this FIFO, all the way down here. That's basically the FIFO code. That's basically assignment 4. But the additional thing is that FIFO in the Chu book is just telling you there's a FIFO, but here we are using the FIFO to store instruction. And what is that instruction? That instruction is the address to register. We have a simple format. Okay, it's like thinking like a processor, but our format is very simple. We have the address, we have the operation, whether it's read and write, and then we have optionally the data. So if it's write, you have to put the data. If it's read, you don't have to put the data. So that is one row of words here going into the FIFO. So now that you've got a FIFO, the control of how the next instruction or the next memory access will now be under the control of this control logic system, where when you have done doing the previous row column access and everything has been sent out, the control system can actually go to the FIFO and request for the next one. So the big difference here is without the FIFO, the CPU will just keep sending you stuff, and then you actually have to have a signal to tell the CPU to stop. Okay, but it's not great. If you tell the CPU to stop, then what's the CPU going to do? Is it going to wait on you or what, right? So it's like you don't actually want the CPU to wait too long, right? If it's got a memory request, then it's got to figure out, maybe it can run some other instruction while waiting for your memory request. Okay, so but then you also don't want to be able to halt it. So the way you handle this is you put in a FIFO, and you can control the depth of the FIFO. That means how many memory locations you want to store. Okay, and then that has something to do with the rate in versus rate out. Okay, but what I'm just saying is that the FIFO is a way for you to decouple, so the CPU just need to keep sending instructions at its own pace, and you on the memory controller side, you can just retrieve the instruction at your own pace once the DRAM has completed one instruction and all that. And this kind of FIFO thing is kind of nice because the whole top part here, you can consider it as one bank. Okay, one bank. One bank meaning that there is a bunch of resources you need in order to perform one transaction. One transaction means one memory access, whether one read or one write. Okay, and then if before that transaction is completed, you have to wait. Okay, that's why it's called one bank. But to illustrate the concept of parallelism, we typically have more than one bank. So here it is very simple example in our ADSD. I give you a two-bank design. Why do you have to do a two-bank design? Because you know that once you're processing one transaction, which is You have to do the row access, the column access. You have to wait for all those times that you've seen in the state machine. Let's say another memory request comes in. If possible, you hope the memory request would go to a different bank so that this one, while it's processing, you can initiate the processing in this bank. Then when the result is done here, the result here also done. So this is like parallelization. You are using two different resources in parallel. And that is the way you hide latency, right? Because the row access, the column access, all these are latency. These are all the delays you have to go through every single, you have to go through the base address register, the decoding, the base address register, the address counter, then activate the row, then activate the column select, and then only you do the operation on the DRAM array, whether it's read or write, then only you're done, right? So that there's a sequence of things that you need to do that take time. But if you happen to require data that is stored in two different banks, so this is called one bank, this is called another bank, two different banks, you can actually process that request, that transaction in parallel. Okay, that's why you have two FIFO streams. Okay, so that what you're doing is you're saying that I need to partition my virtual memory lah. That means if your memory is from location 0 to 16, maybe you have 8 locations in this DRAM and another 8 locations in this DRAM, and you try to arrange it in such a way that most of the, if the CPU is making memory accesses, you hope it will request memory from both these arrays nah. And then in this way, you can make it appear like your memory is faster. Why? Because you are doing accesses in parallel. While you're accessing in one bank, you can start the request to another bank, and then the result from one bank come out, then the result from second bank come out. So it's like you get two results in maybe slightly more than the time it takes for you to get one result. Okay, so this is how we actually get the illusion that memory is very fast. And this scheme is called bank interleaving. It's a form of parallelism in circuits, right? So most of the time, the concept is the same, is that you actually have a bunch of replicated resources. Because you look, the circuits are exactly the same. But there has to be some decision whether you are sending the request here to this FIFO or you're sending the request to that FIFO. And that comes to the last assignment, which I'm still working on, but I'm going to get it to that. That is basically you actually have a system where this is coming from the CPU. A single CPU is this arrow lah. A single CPU can use a crossbar switch, which is exactly the same like what you've seen in VLSI. It's the same thing. Okay, that crossbar switch that you have the circuit in VLSI, this is that same crossbar switch, except the crossbar switch of 1 to 3. This is a 2 to 2 crossbar switch. So I'm just going to talk about the first input, because this first input is coming from one CPU. If it is going to the memory addresses in this bank, the crossbar has to select this bank and send it to this FIFO. If it's going to this bank, the crossbar has to select, send it to the FIFO. So you have a simple scheduler circuit that will just check this address. Is it belonging to here or here? If it belongs to here, you will just switch the multiplexer to go here. Belong to here, switch the multiplexer, go here. And this scheduler is not the fixed priority arbiter that you saw in VLSI. It's a bit different. It's just going to look at, the scheduler is just going to look at the address. Does it belong to the first group or the second group? Depending on how you arrange, it's just looking at, because it's 2, you just look at 1 bit of the address only, okay? All right, so that is the part how we are handling resource allocation. So this is a form of resource allocation circuit. It's a form of arbitration or resource scheduling. The big word is resource scheduling. So you're sending an instruction, you have to schedule the use of the crossbar. That is, this input is going to go to which particular branch of resources, okay? And you schedule for that. And we make this problem a little bit more complex because now I'm saying that this same memory system is being used by 2 different processors. So the scheduler now has to figure out 2 different processors are going to address the same memory area. Who is it going to give to? So this makes the schedule a little bit more complicated, because if branch 1 is accessing this one, branch 2, the CPU 2 cannot access this one at the same time. It must store into the FIFO first before this one can do that. Okay. And here what we're saying is that you see the FIFO is a nice like a buffer, because only when the buffer is full, it will send a response to the scheduler. And you send a response to the scheduler will just tell the CPUs, you are not granted access to the crossbar. Therefore, you have to wait. Okay. So you are still having a signal that tells the CPU to wait, but the signal is at the, what we call it, a coarser granularity. Like you will tell the CPU to wait in far fewer instances than if you didn't have this FIFO and this crossbar and all that. So FIFO is a way for you to actually, it's a load store, it's a form of a load store architecture, right? So the load store architecture that you're probably used to is the one that you learn from computer architecture in UTP, the undergraduate, where you store the instructions in RAM, in memory, then you go to the address and you fetch that instruction, okay? I want you to recognize that the FIFO is also the same thing, except that in the FIFO, you don't actually have to specify the address. It's just the next instruction that's coming out. So it is still a load store architecture because you are loading the instructions here. Okay, you are storing the instructions here and you're loading these instructions from the unit. Okay, but sometimes the FIFO is also called a producer consumer architecture. The producer is the one that is feeding in, the consumer is one that's taking out. Okay, so the FIFO is a load store architecture as well. You are storing and you're loading, and that is used to actually give some breathing room and not restrict too much your producing units here. And then we have this crossbar and scheduling system. So the crossbar is an interconnect. It's a kind of connection. As we mentioned, there are in general 3 major kinds of connection. You have bus, you have point-to-point, and you have crossbar. Okay, crossbar is somewhere in between. Point-to-point means this one will have its direct connection here, this one will have its direct connection here. So you will have 4 lines connecting. So it's not too bad if you have a two bank, but if you have 8 bank interleaving, then you will have 1 CPU will connect to 8. Okay, then 8 CPU connect to 8. Then each of these resources will have 64 connections going to it. So you got 64 FIFOs for each bank. So the resource scales up really, really fast. So point-to-point is good in certain ways, but it really takes up a lot of resources. And bus is not so great because bus only one resource can talk at the same time. If for instance I have this one and this one connected on the bus, if this is accessing the first one, this one cannot do anything. But with the crossbar, if this is accessing the first one, this one can access the second one, but it's just not allowed to access the first one. But for point-to-point link, this and this can access the first one anytime, but you're still going to be limited by the use here. And in assignment 5, basically, we're looking at this process of actually loading this instruction, fetching this instruction, which is nothing else but the address, the data, and the read-write, whether it's a read or write operation, the decode, the execution, and then update of the memory. That is pipelining. So that one you will actually go to break up all these resources in pipeline. So you put registers in front so that while this is being updated, you can still use the row decoder to access another operation. Okay, so I'm just going through this. I will go through this again at a later point in this semester. Basically, another 1 or 2 weeks, I'll go through this again once the assignments are up to complete. But I just wanted to show you how this is the big picture. We are combining for a complex digital system. Okay, all these are all the parts, and what you have in the Chu book is more like the basic components, but the basic components are all important. Okay, so here you can see how to access synchronous dual port RAM, but this is SRAM. SRAM is just static RAM. SRAM you don't have refresh, right? And you don't actually have a row buffer. I call a row buffer at all. Why? Because SRAM basically it will hold its value as long as there's power. It's a 6 transistor cell, so that's why it's called static RAM. It's used for caches and all that. Block RAM, I think maybe yes. Block RAM is a special RAM under FPGA. And here is a simpler yes, SDRAM. This one is actually a module for SDRAM controller. Okay, so but they're using a little bit more So the transaction management circuit, that is how I'm giving you one simple version, which is the FIFO and the crossbar and all that and the command engine and all that So you can look at this a little bit. This one they talk about a conceptual circuit, but they don't actually give you the actual circuit for it. I don't think so. So they just give you a call. But you have to understand that what we are actually designing is we're designing this whole thing. Okay, that block that I showed you in the PowerPoint just now, that's this whole thing. It's an SDRAM controller plus the SDRAM part itself. Okay, so we're taking it as a basic block, not an SDRAM, but the the DRAM itself. Okay. Okay, let me go back. So part 1 is basically where you get all your examples and all your questions lah. Part 2, part 3, part 4 is bigger system example. If you are interested, you can also look at it lah. Like this, it's got some interesting circuits like the UART, Universal Synchronous Receiver Transceiver lah. This is basically a serial port driver lah. Okay, you can actually see how it's designed. But for the purpose of really understanding the basic, is enough for you to actually go through part 1, Alvin. Part 1, chapters 3 to chapter 6. Chapter 7, if you want to understand a little bit more, and chapter 7 is more the FIFO, is interesting. Chapter 8, if you want to go a little bit more depth into the best practices for Verilog. So this book itself, Chu book itself, is more than enough if you were to follow it carefully. Okay? Is that clear, Alvin? Do you think that's helpful?
Yes, yes.
Okay, now I'll mention another resource lah. Yeah, so yeah, this is unfortunately this is the way open distance learning is lah. We give you the resources. You need to put in the time to learn through it lah. But as I mentioned, I'm available. I can have additional tutorial session with you if you're stuck in any of these things lah. So I want to also give you this other resource. Professor Bill Daly is actually a professor of computer science at Stanford University lah. He was the, I think he still is the chief scientist in NVIDIA designing, and he built some supercomputers in MIT lah when he was a professor there. So this book is great, talking about all aspects of digital circuit design. I would say maybe you can start with chapter 7, okay, because chapter 2, 3, 4, 5, 6, this is basic digital systems design, except that maybe if you like, you can read chapter 4 and chapter 5, because that one probably was not covered in UTP. But I cover chapter 4 in VLSI actually. The switch model, the idea of using switching logic is actually from chapter 4, is the Stanford view of looking at CMOS transistors. Okay, so you can actually read chapter 4. And chapter 5 basically is talking about the delay, the logical effort that is also in VLSI. So chapter 5 here also is a different approach for talking about delay using logical effort. So you have logical effort, fan in, delay calculation. So you can read chapter 5 as well as an alternative to the Harris book. Okay, but for Verilog, chapter 7, chapter 8, chapter 9 is probably a more traditional way of doing advanced digital circuit design. So you will notice in more earlier textbooks, earlier textbook meaning like those that are like 4, 5, 6 years ago and earlier, when they talk about digital system design, they always ask you to do adders, multipliers, and then they have all these look-ahead circuits, booth recoding, dividers, complex multiplication, floating point adders. I've taken a very conscious decision not to cover these circuits. Why? Number one, I consulted with Intel and some of the designers. Everybody agrees on the same point. This was the expertise they needed about 10 years ago. You need to be able to design all the complex logic to go through all the paths of all these complex circuits for computation. These are arithmetic circuits for computation. But today, the bottleneck is not in computation. And today, if you join any design company, most of the big ones, they already have standard circuit. They have like 5, 10, 20 different proven designs of all these arithmetic circuits, optimize everything. Today, what they actually need is to worry about how to transfer data between circuits. That's why memory interface is very important. They need to be able to manage how do you allocate data to which resources. That's why scheduling circuits are very important. And this you see in routers, you see in modern processors, multi-core processors. It's basically you have parallel units of resources. You need to be able to activate which one at a point of time. That's why the scheduling is important. Interconnect is important. And again, this idea of bit slicing on it. That's why the course is designed this way, because we are trying to be up to date. So it's not necessary. So don't feel too bad if chapter 12 and chapter 12 and 13 are a little bit complicated, because designing arithmetic circuits is the most complicated part about combinational logic design. you want to become an excellent combinational logic designer, you should be able to design arithmetic circuits. They're not too bad, but they involve a lot of mathematics to see how to optimize. So you can look at them, but don't feel bad if you are not able to solve them for this class. I just provide this material, you can download it, you can read it in your own time, part of your self-development after the masters is okay, right? Just letting you know, don't feel too bad, but all his examples here, this whole book, every example he has of circuits, he has the Verilog equivalent. So that's why this is a very good book. Okay, so you have the combinational building blocks. He gives you some combinational circuits, arithmetic circuits, binary, this one, and then he has this tic-tac-toe system. Then he has a floating point and fixed point arithmetic. But the sequential logic is important. This one is a state machine. He shows you how to do state machine and also how to do Verilog on that. And timing constraints is what we'll cover a little bit after this today. And basically, I would say if you want to look at this chapter, you probably look at chapter 8, chapter 6, chapter 7. You can start from chapter 7, chapter 8. This is probably good enough in terms of, maybe chapter 9 if you want, probably good enough for combinational logic. And you can look at chapter 14, chapter 15 for sequential, chapter 14, chapter 16 for sequential machines, state machines, how to do Verilog and all that. Again, he has examples and he also has exercises, design exercises, plenty of things for you guys to do. Okay, chapter 17, 18, 19 are a little bit more complicated. Okay, chapter 17 is basically how do you break up your finite state machine, how do you design the states. Okay, I've taken a different approach in that chapter 17, basically you're doing in assignment 2 already. That's the factoring the finite state machine, how to decide the states. Okay, so you are learning that by doing. But chapter 17, that's actually that. And chapter 18, this idea of microcode is very interesting because it's the idea that the state machine is actually programmed as a load store instruction. Okay, here's the idea of microcode. Microcode is you still have a state machine, okay, but one instruction. So you have your decode instruction, right? So you have your main state machine, which is decode one instruction, then go back decode the second instruction. But each instruction is a bunch of mini states, and the mini states is actually coded in memory as load and store. That's how you actually can have a flexible microcode. That's microcoding. We are not going through this in example. It's a very specific way of doing design. I would say it's a little bit old-fashioned, but it's still in use today for flexibility if you want to flash in. But we're not going to do that. System level design, this is important, 20, but you can read it. Okay, the system design process, especially the partitioning. This is how you break up. Let's say you have a certain specification. How do you break up? Here, the breaking up, I show you by example. That is through the 6 assignments we have. I show you how the partitioning of the design is done for a real-world complex design. But the basics, you can also look at 20 because these ideas are a little bit hard to grasp unless you actually do a real design example. And number 5, assignment number 5, we're going to be doing an example on SDRAM pipeline. But you can also reference to 21, chapter 21 to teach you about the pipelining approach. Don't worry about asynchronous sequential circuits. That's a particular form of state machine design using latches, not using clocks. Basically, I'm not going to cover that because that's its own set of problems. And today is actually recognized, although you can do asynchronous sequential circuits, maybe you can save a little bit more on power. The saving is not that much greater, and most people will agree that the simplicity of synchronous state machines, clock D flip-flops, is good enough. Okay, you can learn more about flip-flop, not necessary. Method stability and synchronization failure, I'll briefly cover today. You can read more detail here, but it's more of just for you to understand what is it. And the reason you need to understand what is it, because this is what will set your timing constraint. Why we have the setup time, hold time, and all that is because of metastability and synchronization. I'll have a very straightforward way to explain this to you. I've tried to simplify this as much, but here has a gory math. How do you estimate probability and stuff like that? Synchronizer design. This is actually a method to overcome metastability. Okay, and basically here again you see one of the key uses of FIFO. Besides load store, first in, first out, FIFO is actually used to to prevent and to recover from metastability. Let's say if you have a totally asynchronous signal going into a synchronous state machine. Asynchronous means maybe you have a signal from some external sensor, it's not clock or something like that, and it's just going to go through the synchronous state machine. You might have problems. And then Appendix A has Verilog coding style. So I think between the Delhi textbook here, as well as the Chu textbook, you have so many work examples and so many exercise questions. So yeah, if you can even go through one book, it would be good enough really actually. But if you are not able to understand from reading one particular book, you can actually read the examples from both books. Okay, so that's okay as well, right? Okay, Alvin, I hope that answers the question.
Yeah, that's good.
Okay,
It's just
so
at the Verilog, I've never been. I never did it before, so it's a lot of gaps to.
sure. So I understand that, and that's a little bit of a challenge here, lah, because the way you are sort of taught programming, lah, and the way most students think about programming is, oh, I need to spend months to learn a language. Okay, that's the way C++ was approached. But I like to encourage you to take a different idea of programming. Programming is just a language. Okay, what you need to understand is how do you express yourself in that language. So Verilog, the fastest way to do it really is to look at example of what kind of circuits are built. So there are actually two challenges here. One is the actual circuit design, which is hard. You need to grasp that concept. How do you actually design circuits? Because you're probably just used to just the K-map way, and then you're just like, I just follow the recipe, I'll get a design. But that's pretty much useless lah, because as I told you, the largest circuit you can build is a 6-input circuit, and who builds 6-input VLSI chips nowadays? Nobody does that. You are talking about hundreds of thousands or tens of thousands of signals. So you really need a different approach, okay? So the first competency is how do you design the circuit? Like how do you design the logic? Okay, how do you design the selection? And I try to give you a recipe that is ask the question using truth table and multiplexer, right? I give you that multiplexer example in the state machine. Okay. The second is actually how do you write Verilog. So actually most students' coding problem is algorithm rather than syntax. But you all sort of think that it is a syntax that difficult, but it's not. It's the algorithm. So what I'm trying to point out is it is the design here that is difficult, not the code of the Verilog. If you understand the Verilog patterns, how to code, and if you have your design, you can write the Verilog already. So I'll just give you an example. You just take some of the circuits that are already drawn in the Chu and in the Delhi book. Then you test yourself, you just write Verilog code to describe that circuit. After like, I think your 6th or 7th circuit, you will know how to write Verilog already. But you're still stuck on the problem, how do I design a circuit? And that one, there's no other way to learn than to actually try it yourself by trial and error, and to actually go through and observe and read how other people actually do their design. That's why there's so many examples given from Chu and Delhi, and you have the ST-RAM example. And I actually don't ask you to design from scratch. I give you a base code and then you have to modify it. Yeah, that is the philosophy. Okay, yes, it's a little bit scary because maybe it's your first semester and you are maybe not that used to a little bit more independent learning. But again, as I mentioned, I'm here to handhold you a little bit. So, you can ask more questions if you want a little bit of a leg up or a hint. I can kind of point you towards that. Okay.
I think it's okay so far. I was able to catch up Verilog. Just that if given a new example, so it might be a challenge. But I was managed to get the first assignment done.
Wonderful, wonderful. Making progress. You're making progress. I just want to encourage both of you that this feeling is, get used to it lah. That's lifelong learning feeling. That is, the longer you're in your career, and if you are lifelong learning, you will understand and you will recognize this feeling. Like anything, it's almost going to come everywhere lah, because you're in a high technology business, a high technology company. So you start looking at all this technology, like, oh crap stuff. But The important point is to understand the principles, and things take time, and you make small progress every day. You won't see your progress on the day-to-day so much, but you will see your progress on a month-to-month. You will find that maybe now you probably spend about a month on this already. You probably, if you look back, you can say, oh, before I started this, I didn't know how to do all this, but now I know how to do all this. So these are things to just encourage you. Okay, so keep at it. I'm sure you are making that progress. Keep at it. It's consistent work. And again, just offering, yeah, please ask questions. We can have more sessions that I can clarify on your doubts. Okay, do you have anything more specific that you want to address, me to address?
Okay, about the second assignment, the bit slicing, I didn't actually get the question clearly actually.
Okay, understood. Okay, let's go to the second spectacle module. Let me read that again and see what exactly they ask you. Okay. Okay, I thought I opened. Oh, I didn't open it yet. Okay, let me open this Word document. Okay, then let me share this, the Word document. Okay. Complete this. Second assignment. Oh, this is assignment 1. Sorry, wrong one. Assignment 1, assignment 2. Okay. I see. All right. What actually I given you here in this read-write circuit example?
No, sorry, doctor, not this. This is the first assignment. The second one I think is in the ULearn X.
Okay. Sorry, I'm not showing you. Yeah, I was quite ahead of myself. I'm actually referring to this lah. It's module 3, but it's assignment 2 here, right? This one, right? The bit slicing. Can you see my screen?
Yeah, I can.
Yes.
Yeah, this one, right? Okay. So this one, I've given you an example of the SD-RAM circuit lah, which is the counter, and the multiplexer for column select. Okay, the base counter and all that lah. Okay, but what I've done is that circuit is only for a DRAM with 1 bit. Okay, so I'm asking you to design this, to modify this design so that you make the whole bank. Okay, and that is utilizing the bit slice concept lah. So let's talk a little bit about what that means lah. Okay, so if you look at the SD-RAM system, what I meant to say is I've given you a circuit. I've given you some base code for something like this. Text DRAM. I've given you this blue one, row decoder, row buffer, column select, address counter, base address register. I've given you this circuit, and I want you to convert it into this orange circuit, which is a bank. Okay, because if you look at this DRAM, I can partition this DRAM into a bunch of boxes, right? A 2-dimensional box, right? So I can select a row, which is giving me a whole set of values here. And then I select a column that is going to give me 1 value, and that 1 value is 1 bit. Okay, is that part clear? That I'm giving you a DRAM that is giving you 1 bit. Do you understand the row and column way of looking at things? Okay, so let's say you have an address. Let's say I have a 8-bit address. Let's say 7 to 8-bit address, bit 7 to bit 0. Okay. And then I have a memory. Let's say I have a memory. Okay, let me simplify it. I will just use 4-bit address lah. I'll just use 4-bit. I have an 4-bit address. Okay. Okay, so this is my table design. Let's go to okay. This table here that you can see, that is my DRAM, okay? And I have 4 bits here of address, okay? So I've bit 1, bit 2, bit 3, bit 4, or use B lah. Bit 1, bit 2, bit 3, bit 4, okay? So now assuming I just have bit 1, bit 2, this gives me 4 combinations, right? Am I right? Do you understand that?
Yeah.
Yeah, okay. So if I have 4 combinations from 2-bit, I can select between this one, this row, this row, this row. Lah. I can select between 4 of these rows. So 2 bits of address will give me the row position, and 2 bits of column will give me these 4 columns, correct? So my address is 4 bits. 2 bits are used to address which row I am in, and 2 bits are used to address which column. Lah. So let's say this is address 0. Address 0. Address 0 has maybe data, and maybe address 1 has data 0. Address 2 has data 1. Address 3 has data 0. 4 has data 1, address 5 has data 0, address 6 has data 1, address 7 has data 1. Okay, why am I doing this? I'm doing this because I'm showing you one way of laying out the address. Okay, address 0, all these yellow color one, that is the address of that box. That's how I'm going to access that box. And I'm labeling the address this way, either all the yellow ones. Okay, so if I want to address 4, for instance, that means I have to get 0, 1, 0, 0. That's address 4, right? So 0, 1 is the first row. Sorry, the second row, right? This is 0, 0 row. This is 0, 1 row. And 0, 0 is the first column. So this whole address gives me this value, but the value stored in each of these is 1 bit. Okay, 1 bit. Now, can I do it the other way? Can I actually do it, call it this way, and then have this to be address 4, address 5, then at 6, 7, then address 8, address 9, then address 10, 11, address 12, address 13. Can I do it this way? Can I arrange it this way? Of course I can. In this case, just now, this was the row and this was the column address. If I change the naming scheme here like that, then it's different. Then now, in order to access this particular one, I need address 0001. Then this becomes the row and this becomes the column address. Okay? So this is nothing else but basic 2D DRAM arrangement. You understand this part or not?
Yes, I get you.
Yes.
Okay. Then you can start thinking it doesn't have to be this boring. You can actually have something like this. So now, how many bits for the row? How many bits for the column? Okay, can you tell me how many bits for the row? How many bits for the column? Sorry, can't hear you. I think you guys are mute. So let's say I address this address location. How many bits for the row? How many bits for the column? So in this case, it is 3 bits for the row, 1 bit for the column. It's still the same address, but my arrangement is different because my DRAM partitioning is different. Okay? Do you understand this?
Sorry, Doctor, I don't understand.
You don't understand? Okay.
Yeah.
Okay. Okay, good, good. At least you asked, huh? Okay. Okay, just now, I had given you a 4x4 memory like that. Okay, I given you a 4x4 memory like that, right? That one was, I told you, a 4x4 DRAM. Okay, that one, the address is the same, right? Okay, right. How many locations are in this 4x4? 2x2 memory. How many? Sorry, this 4x4 memory. How many locations are there? How many storage locations are there?
16.
16, correct. Exactly 16. So I have 4 bits can give me 16 combination, which means I can get 16 locations lah. And then the way I partition is I take 2 bits of the address, I can address the row, 2 bits of the address, I can address the columns. Okay. Now, in terms of the capacity, this box and this box, do they have the same number of boxes in them?
Oh yeah, same.
Is you can see it's same, right? It's
Yeah.
16, except this is 4 rows times 4 columns. This is 8 rows times 2 columns, correct?
Right.
So if they are the same number of boxes there, it should be the same address can address them, right? That means my address of 4 bits can address 16 locations. So I can use a 4-bit address to say which location here that I want. And I can use that same 4-bit address to address which location here I want, right? Same, right? Okay, but what is different? What is different is this particular DRAM has 8 rows and 2 columns. This particular DRAM has 4 rows and 2 columns. Okay, that part can see how it is. Do you understand that? Okay. Now, what I'm going to do is I'm going to ask you to assume that, and it's not just assume it's true lah. Each of these box basically is a capacitor. It's literally a capacitor in DRAM. Okay. Let's draw this. Okay. So this is literally single capacitor. Ayo, insert shapes. So insert shapes. Draw. Insert shapes. Shapes. Well, it's literally a capacitor connected to ground like that. Okay, and the capacitor can store 1 bit, right? Either it is charged to VDD or it's not, is discharged 0, right? 1 and 0. Understand that?
Yeah.
That's how the DRAM is organized. Okay, so when you select one row here, what you're doing is you are just saying all these capacitors are connected to a buffer down here. There's a buffer that's called something called a row buffer. Okay, that we talked about briefly. I think I mentioned it briefly. So there is a row buffer. You can think about it as a very crude way of thinking about it. This is a row buffer, okay? You can either put in the first row to put inside here, the second row to put inside here, the third row to put inside here, the fourth row to put inside here. It's some sort of like a multiplexing circuit, but it's an analog multiplexing circuit, okay? So the row is actually telling which of these row of capacitors are going. So you can think about this row buffer as 1 flip-flop, 1 D flip-flop, 1 D flip-flop, 1 D flip-flop. So there are 4 D flip-flops. The 4 D flip-flops here are connected to some kind of like analog multiplexer where it can take the input from this row, the third row here, up here, the third row, this row, or this row. Okay, and this row is 4 capacitors in one row. Okay, so if you're talking about this row, that means these 4 capacitors that are like, let's say holding what, one value, logic 1, logic 0, logic 0, logic 1, that will be connected here. Okay, if you're putting 0, 0, this row will be connected to all these D flip-flops. If you're putting 0, 1 into it, again, that 0, 0, 0, 1, 1, 0, 1, 1, that is the row address. That is the row decoder. That is this row decoder here is basically selecting which of these rows are going into this set of registers, flip-flops. Do you understand that?
Yeah.
Okay, you understand that this is called the row buffer, the blue one. Okay. Now, as I mentioned, this SRAM, this DRAM has 16 capacitor lah, 16 possible locations lah, or 16 possible ones and zeros it can represent. And at one time, I can activate 4 at the same time and pass 4 of them down to a row buffer. Okay. Now, I can also design my circuit in such a way that my row buffer is only 2 flip-flops instead of 4 flip-flops. So that would be the case of this DRAM. So in the case of this DRAM, I can either take this first row, the capacitor here, I select the row. When I do the row select means I'm selecting these 2 capacitors, which are connected to these 2 flip-flops. Or I can take the second row, these 2 capacitors connect to these 2 flip-flops. Or I can take this 5th row, connect these 2 capacitors to these 2 flip-flops. I can take this 7th row, this 8th row, these 2 capacitors to these 2 flip-flops. Okay. This is slightly different from this. Why? Because here, my row buffer is only 2 flip-flops or 2 capacitors. Whereas here, my row buffer is 4 flip-flops or 4 capacitors. Are they the same DRAM? They are different DRAM, but they have the same capacity. Same capacity. The capacity is 16. Or they can store total 16 bits, right? Because there are 16 locations, 16 capacitors. But the architecture is different. Here, my row buffer is size of 2. Here, my row buffer is size of 4. What this means, row buffer size of 4, means that if I select one row, straight away I have 4 capacitors that I can buffer into here. Okay, but I'm not going to read all of them out one, because when I request a memory location, it's one location, one capacitor. So I'm going to ultimately select one of these capacitor. But this architecture is more favorable to stride. So let's say I mentioned in the example, in SDRAM, the idea is that when you activate this row access, that is, you are selecting this row and connecting it to this row buffer, that takes a bit of time. If you go through the example, the assignment, you will see that takes some nanoseconds, some set of nanoseconds. And then there's the column access. Column access means you're choosing either you sending this box out, this second box out, this third box out, or this 4 box out, right? Because you are requesting only 1 bit from this DRAM, okay? But when you access one row, 4 bits are read out and buffered. Okay, but you are not going to send all these 4 bits out. You are given one address. You have to give the result of one address. So you have to have another operation which selects the column. Okay, which one of these? Okay, so with a 4-bit row buffer, let's say you want to read 4 consecutive addresses here, 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 here. This 4-bit row buffer is going to be faster because you make one row access, which is you select these 4 capacitors and then you send it here, okay? And then subsequently, you can do 4 consecutive column access, which is much faster. Whereas for this architecture, if you want to read 4 locations consecutively, you need to make 1 row access, then you make 2 column access, and another row access, and you make another 2 column access. So you have 2 row access, right? And if the row access is longer, this architecture will be slower than this architecture. Now, do you see the nuance why we actually have different architecture? I've just shown you for the case of 16, but you can imagine you have 2048 rows, which, you know, there's so many configurations you can have. Okay, so what I'm getting you to do is, I'm getting you, like, if I give you a particular configuration, you must know how this is partitioned. Okay, but I hope you can see and you can understand why we actually want to do, why we actually want to have differences in this. Do you understand that?
Doctor, one question.
Yes.
Regarding the architecture, ada two row or for column to column. So in our design, which architecture is the best?
Okay. There's no fixed answer. It depends on the application. Okay, that's why you have different ways. I want you to recognize that if you have this and you need to read 4 strides or more, then this architecture is worse than this. But if you have something that you just want single access memory, this architecture is better. Why? Because the row access time for a row of 4 is going to be longer than the row access time for a row of 2. Why? Because there are more capacitance to activate in the row of 4. But if I need to access multiple rows versus I just read the row once and then do column access, it's going to be faster to pick this one. Okay. So if I have more random access, not contiguous memory access, I would choose this architecture on the left. If I have a lot of contiguous access, means I have a lot of cache hits, like what they call the either spatial or temporal locality that you learn in computer architecture, then I will pick this architecture. So there is no one size fits all answer. That's why you have so many different configurations. Okay, for the purpose of advanced digital circuit design, I'm not asking you to choose the best architecture. That is a computer architecture problem, not a digital circuit design problem. But for the purpose of digital circuit design, you need to be able to understand and design. Let's say I give you, for example, in this case, I give you, okay, let's look at the example question here. I give you a particular memory specification, like you must be able to understand, you must be able to understand how the rows and columns are partitioned. Okay, because I won't actually give you this exact shape. Okay, I'm just going to give it to you in words. So I give it to the words here. Right, I tell you that there's a 8-bit word, 16-bit address. Okay, right. I've given you 1 bit as DRAM, but I said X8. Okay, so you have to be able to infer 16-bit address. 16-bit address means there is 15 to 0. So there is BBBB, 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 BBBB. Okay. The next question is, you must know how the row and column are partitioned. Okay. Do I tell you that? If I actually give you the number of rows, then I've actually told you that. Okay. I believe I've actually given it to you. Do I mention number of rows? Oh, maybe I don't, but maybe in the example here, I will give you inside here in the design, I will give you because here I'm actually want you to do only the bit slicing. Okay, now I'm going to talk about the bit slicing after this, but let me finish up first Maybe in the exam or in some other question, I may actually tell you, you have 2048 columns, or you have 512 columns. Okay, if I tell you 512 columns, you should know how many rows there are already, right? Because 512 columns is 2 to the power of 9. Okay, which means that 2 to the power of 9. Okay, which means that out of 16 bits, okay, out of these 16 bits, 1, 2, 3, 4, 5, 6, 7, 8, 9 bits will give the columns. Okay, so how many bits are remaining to give you the rows? How many bits are remaining to give you the rows?
Sorry, sir. Are you using another screen? Because
Sorry. Yes. Thanks for. Okay. No wonder you cannot see. So I'm just saying, okay, let's say I give you a 16-bit address. I tell you the address is 16-bit. Okay, then maybe in the exam question or test question, I will tell you that there are 512 columns. Okay, so 512 columns. 512 is to the power of 9. 512 columns means there are 500 of these columns. Okay, so for 500 columns, I need 9 bits to represent all 512 columns. So there is, will use 9 bits of the address to represent columns. So I take 9 bits of the address, this covered in yellow, this will represent the columns. How many bits are left to represent the rows?
2, 4, 6, 7.
Very good. So you have 2 to the power of 7 rows or 128 rows. So there are going to be 128 boxes down here, 512 boxes around there. Okay. If I give you, for example, 16-bit address, there are 2048 rows. Okay. How many columns are there? How many rows are there?
Can we divide like 2 and try to divide the rows and columns by 2 for the bits?
What do you mean by that?
If let's say 2048 we divide by 2 is 1024.
No, no. It's actually power. 2 to the power of 12 bits. So 2 to the power 2048 rows is 2 to the power of 12 bits. So actually what you need to do is you need to take log of you need to break this down into a power of 2 lah. So the easy way will be you do 2 times 1. 2 to the power of 1 is what? 2 to the power of 2 is what? Then 2 to the power of 3. Then you just have all of that written down somewhere lah. Then you will be able to find out lah. It's very quick for you to just get the 2 to the powers list lah. Then you just look that up. So 2048 rows is 2 to the 12 bits. So there's 12 bits on the row. That means there are 2048 rows here. So if there are 12 bits, that is for row. How many bits in the columns? Yes.
I think you get the wrong number. 2 power of 11, right?
Ah, yes, you're right. Very good. East is very sharp. Very good. Exactly. See, that's why it's good you have. So to the power 11 bits. So you have 5 bits. This is 32 columns. So there's going to be 32 columns here. Okay, do you get it?
Yeah.
Okay, so now you know how to have these differences. Okay, so far, what we're talking about is I'm telling you how a single 2D DRAM is designed. There are different configurations, okay? And when you access one of these, that means this whole 16-bit address or the 8-bit address will give you only one box, which is one capacitor, which means you only get 1 bit, correct?
Right.
So in this case, this is giving you a memory that is 16-bit address, 1-bit data, right? How do you make 8-bit data? This is how you make 8-bit data. You get a second one, you get a third one, you get a fourth one, and so on. You get 8. Okay, so when you access this first capacitor, when you access this row of the first capacitor, you are accessing the row of all 8 DRAM arrays. Do you understand?
Yeah.
Okay, and so if you have 8 DRAM arrays, you will have 8 row buffers. Each row buffer will have, in this case, 2 lah. But of course, if you're talking about here, your row buffer is 32 flip-flops lah. Okay, so you have 32 flip-flops times 8. Okay, how many row select signals do you have?
Sorry, can you repeat again?
How many row select signals you have? So we went through, I said you need 8 bits of data. One DRAM array will only give you 1 bit of data. Okay, so you need 8 bits. So you need to multiply, you get 8 different DRAM arrays. Okay, then you put it together. Then each DRAM array will need its own row buffer, right? Because it's a different array, we have different data in that. Okay, so now my question is, how many row select signals do you need? Because you're selecting rows from 8 different DRAM arrays, right?
156, right?
No, it's the same row select. Right, because you're selecting the same address. You got it? Okay, it's not meant to trick you, but I'm just actually highlighting all the places where you can get tripped up. Okay, right? So this combination of 8 DRAM array is a DRAM bank. That's the 3 dimension here, right? Because this is a DRAM array. The blue color one is the front one. You times by 8. This is called an times 8 x8 DRAM bank. Okay. All right. Do you get that? So the assignment question is asking you. The assignment question is asking you to design 8-bit word. Okay. Data width of 8 bits times 8. So times 8, this is one bank lah. The bank is 8 bits. So basically, I'm asking you to do exactly just what I told you to do lah. That is, you actually have to replicate. Wait lah, let me change the screen properly. You actually have to replicate that 1D array times 8, the row buffer times 8. You make sure that that same row address is going to all 8 DRAM signals. It's not 8 different row select. It's the same row select going through the 8 arrays, and it's the same column address select going through the 8 row buffers, right? Because you need to select the proper column as well, right? That's going through the column buffer. So that is your assignment 2. You actually have to modify the design so that 8 bits are coming out. That means you will have to have how many DRAM arrays?
8.
Very good. And then you code it and you connect the rows and the column decoders. Okay.
Yeah,
And
sorry.
sorry, let me just finish this, Alvin. Then I got the question. And this is called bit slicing. Why? Because I've already given you the design of 1 bit. You are just replicating that 1 bit and then tying up the loose ends of the logic. So you are using the same design to replicate it to grow the width of the bit. That is the bit slice concept. Except that instead of DRAM array, you can think about it in terms of the adder. So if you design a 1-bit adder, you can actually replicate 8 bits is like you multiply it by 8, and then you have some logic that will connect each other, the carry local head logic. Or for example, if you are doing a data path, let's say you're doing an instruction decode for a data path. Okay, let's say your 1-bit instruction, you want to break it to an 8-bit instruction, you just replicate the thing and then you have the glue logic that connects them. Okay, so this is the idea of bit slice. Okay, Alvin, your question.
Yeah, just now mentioned that there's 8-bit data is 8 arrays, right? But in that each array got how many? Is it 8? Each arrays got 8 rows, 8 columns, or how?
Okay, let's take this example of 16 bits. 16 bits will give you how many combinations?
2 to the power. Oh, okay. Yeah.
Okay, how many combinations is that? 11 is 2048 lah. 12 is 4000. 13 is 8000. 14 is 16. 15 is 32. 64,000. So 64 times 1024 lah. Okay. That number of combinations. So that's the number of boxes in a 2D DRAM array.
Okay.
Okay, you got it?
Yep. Okay, got it.
So this part you should go through over and over again because this is what's tricky about DRAM. Okay, because there are different ways you can organize this. And then again, it's not necessary that, you know, like I told you, you can actually have 0, 1, 2, 3 like that, or 0, 1, 2, 3. The address can actually be row wise or column wise. And to make it more complicated, when you start doing interleaving, address 0 can be here, address 1 can be here, address 2 goes up to DRAM, address 3 goes down here. Okay, that means your interleaving is by the last bit. Or you can do address 0, 1, 2, 3, 4, 5, 6, 7. Or you can do 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, right? There's so many ways you can do the interleaving. That's a computer architecture question. Okay, but you need to be aware of that. And if the specification tell you that way, you have to be able to design it that way. You understand?
Yep.
Okay, this is not difficult, it is complex. Okay, there's two two separate concepts. Last time undergraduate, maybe you said susah, 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 difficult. Okay. But I want you to distinguish between complex and difficult. Difficult means there's no answer. That means you don't really know what is the right step. Complex means there's an answer, you know what it is, but it's easy to make mistake because you have to take into account so many factors, so many different details. So something that has a lot of different details and all that, we call complex. Okay. Something that we don't really know the solution, we call difficult. Okay. So these kind of system level problems, they are complex. But once you sit down, you have a systematic way of really working through step by step, you can manage this complexity. So system level design, most of the time it's complex, but you really know how to do it already. It's just, you may get confused because it's complex. So if you get confused, I'm trying to share with you that you go down to the basic concepts. The first is, if you cannot think about 16-bit address, think about 4-bit address. How many boxes? That's why I walked you through the steps just now, right? Because this is the way to break down the problem into manageable chunks and to build your understanding so you can handle the complexity. All right?
Yep.
Okay, guys, more questions on this? So far, do you have more questions? Anything on digital systems design?
I think should be okay. So for the extended assignment, we will the concept will be something like designing a DRAM or something like more.
Something like that lah. I'm
Uh,
not sure whether it's a DRAM, an SDRAM, a combinational circuit. I don't really know, or rather can tell you what it is. But suffice to say lah, I will give you a complex enough question that you will use all 6 modules results to do it. But it may look a little bit different or pretty different from what you see here, but the concept is the same. It's going to have a combinational sequential aspect. You're going to have to use parallining. You're going to have to use parallelism. You're going to have to use the load store FIFO. You're going to have to use state machines, and it's all one design or 2 designs like that. Then maybe you have to get the Verilog. You have to draw the design diagram. You have to prepare the simulation, and you actually have to work through the examples. Like either you simulate with the software or you work through by hand. It doesn't matter. Same. You have to actually show what are the examples of the sequence that you have to test your design, because not just design is important, you have to figure out the test bench, which is what are the specific data that you have to put in order to test all the corner cases, or at least most of them lah. You don't have to be perfect, but you have to show me you understand that you have to cover all these sort of cases, and you give me some examples like that lah. But since you have 24 hours, you do have actually quite some time lah to do that lah. But you need to be, you cannot assume that you have time to learn how to design when you get into the extended assessment assignment. You need to already know how to design and how to write Verilog, how to code, and then that time will be actually spent fruitfully doing the design. Okay. I'm not so mean. I think the design should be able to complete within 1 day lah. You still have time to sleep and all that lah. Okay, and I actually recommend you should try to submit a little earlier before the deadline lah. Okay, before the timeline because I really like all the, there are quite a lot number of papers at the same time. So if you submit like 5 minutes before 9 a.m., 8:59 a.m., you might not actually get to upload to the server lah. Okay, and then if the time close already, then there's nothing I can do already because you need to formally submit there lah. Okay, but if you want to have a backup, you can submit also to me by email lah, just in case lah. But most likely I have to consider your submission on through the Ulen X lah. Okay, and you only allow 1 submission, so be very careful lah. Okay, but like I said, in the worst case lah, if you made the mistake, you submitted, you want to change something, it's still within the timeline, send it to my email mailbox. I'll see if I can try to excuse you under the system lah. With the timestamp and all that lah. But supposedly the protocol is you must submit to Ulen X, only 1 submission allowed. Yeah, can lah. Okay.
Okay.
More questions, guys? If not, then I will start on the clocks, the timing. Should be okay, right? So just give you another 1 or 2 minutes to think about it while I talk a little bit. So you guys are probably already done assignment 1. I know Alvin is done. Is probably you submit soon enough. You can go ahead and start assignment 2. I would likely be ready with assignment 6 sometime soon. That you can go ahead for that. Assignment 4 and 5, Mr. Low is actually working on it. But I think that will also come out. But not to worry. Like if you don't see this module 4 and 5 yet, you go ahead and finish module 6 first. 4 and 5 will come up pretty soon. We'll make sure of that. Okay. So just go ahead and finish that up. And then again in parallel with SI. So these 6 practical modules, I guess for intents purposes, is just 5 different assignments. That would be enough. That's all the deliverables for digital systems design. Okay. Okay, are we ready to start the session on timing? Okay, so what I'm going to do is I'm actually going to talk about timing and synchronization. You can see my slides, right? Can you see my slides? Okay.
Yeah.
Okay, here what I'm actually going to cover is the big branch is what we call static timing analysis. I'll go through all these slides, but basically the key idea is this. The key idea is this. We are talking about synchronous state machines. So you have flip-flops like that, and then you have some combinational logic. Okay. And the flip-flop here will clock something, and then the combination logic will calculate, and then it has to arrive before the next clock, right? In order to go through the flip-flop, right? We went through this in the first tutorial interactive session, right? You remember this, right? So this literally can be in space or in time. But what I'm saying is that basically there are some constraints that we were talking about, that this has to arrive here before a certain time. But it also cannot be too quick. Too quick will be like it will pass through here, and then you will just pass, instead of actually passing through here at 1 clock cycle, it will go through all the way to flip-flop 2 in 1 clock cycle. This is called a race condition. Okay, so today the goal is actually to explain to you what exactly is the nature of this race condition, what exactly is this nature of these constraints, and this is what sets our timing constraints in a design. And why does it arise? So we'll go into a little bit more depth about the nature of flip-flops and why we call what we call the transparency window. That is the window on which data can get through the flip-flop from here to here. What you actually study is you actually study that the data changes instantaneously at this edge. Okay, but you'll realize now in practical design, this is not a straight vertical line. It is actually a slope. So the clock edge actually takes a finite amount of time to change, which means that the flip-flop can actually change within this duration. It doesn't change instantaneously. There's a finite duration of time which it can change. Correct or not? Do you think you can accept that? We'll talk about it a little bit more. Do you think you can accept that? That the flip-flop actually doesn't change instantaneously at the clock, but it actually can change like within this window. Do you agree?
Is it possible, sir?
Okay, I think you want another example. Okay. Okay, let me give you this example. Okay. Okay. Now what we are discussing is how does the flip-flop actually get the output? Okay, how does the flip-flop actually, how are edge triggered flip-flops created? Okay, so now this is not this whole system here, this is a flip-flop, but this D and Q G, this is a latch. Okay, what is a latch? A latch basically is a circuit where if the G is this G, this is the signal. If this is high, whatever is at D will appear at Q. Okay, so now let's look at this output star. Output star is here. So when G bar G bar is high. G bar here is 0 means it's high, it's enabled. You look, the star will actually follow D exactly. Okay, like that, star. So when this is enabled, okay, because it's G bar, right? When this is enabled, you see star, the output will follow D exactly. You can see my cursor moving, right?
Yeah.
Okay, you see this follows exactly. When this is enabled, this follows exactly. Okay, so this is a latch. A latch means if it is enabled, the output follows the inputs exactly. If it's disabled, the output holds its last value. So the example is disabled here at logic 1 because this is G bar, right? You see the output was last at logic high. It holds this value irrespective of the input. The input D changes, it doesn't change. And again here, it holds the last value. Last value is 0. Then it shifts, it disabled. So you see the input changes, output don't change. So the goal of the latch is when it's enabled, whatever is the input is at the output. When it's disabled, it just remembers the last input. Okay? Ken? Do you understand what a latch does?
Yeah.
Okay, that's a latch. Okay, so if you see a SR latch, you see a SR, the symbol is a SR latch, the 2 NOR gates cross coupled or any kind of latch. When you see latch, that's what a latch does. Okay, when it's enabled, whatever's output, input goes into the output, everything. When it's disabled, it just remembers its last held output value. It remembers that. Okay, so we've already gone through this star, what is the pattern, right? Now let's look at this second this second latch. Okay, this star here now clock G is this is positive lah. That means it's enabled when it's logic 1. This is enabled when logic 0 because of the bubble here. This is enabled logic 1. So now we have to look at Q. Q is the output, star is the input lah. So star is the input, Q is the output. Okay, when is logic 1 is enabled. Okay, so it's logic 1. Q will follow star. So Q now following star equals logic 1. And clock 0, logic 0, Q doesn't, it just maintain its previous value. And then when it's logic 1 is enabled, Q will follow star like that. Okay. So now you get the pattern of Q and D. So now we're going to forget all about these latches, these two latches. We're going to consider that these two latches is a age-triggered D flip-flop. You just look at D and Q and the clock. You look at D like that, you look at the clock, oh, it just seems that the effect is that at this clock edge, Q will take on the value of D at the clock edge. So here, the value of, there's no clock edge here, right? It's a negative edge, right? So at the positive clock edge, Q will take on the value of D, which is 0. Okay. So this is how age-triggered flip-flop can be thought about. It is 2 latches. Okay. Okay. So it seemed like I just sort of gave you a magic trick, right? It's like, whoa, what just happened, right? You know, I just walk you through latches, enable, disable. You can understand that. Suddenly, I just point out to you that, oh, you just invented a age-triggered flip-flop. But the key point I want to actually show you here is these latches, when I said enable, means there is a window in which the output will follow the input. And then when it's disabled, you just remember the output, right? So there is a window called the transparency window. Okay. Now, since the basic component is a latch, it appears as if it's an age triggered, but it's not fully an age triggered. Why? Because there's a period of time where this flip-flop, okay, what happens, you look at here is like you are remembering your D is following whatever value here, and then this value captures it, then after that is passing out here. So it's like this is enabled, this is disabled, then instantaneously this is disabled and this is enabled. Okay, right? That's what we're talking about the clock. In reality, this is not enabled and disabled instantaneously, right? Because the clock, as I mentioned to you, there is a slope. So there's going to be some period, some small window in time where this is not yet disabled, it's still enabled, and this is enabled, not yet disabled. This is not fully disabled, it's enabled. Okay, so there is some small window in time where you can change this and this output will also respond to this change. Do you understand that? And the reason I'm mentioning this to you is that in theory, if the clock is instantaneous, this one will disable, this one will enable exactly at the same time. Then this one will enable, this one will disable exactly at the same time. So it means that this one change will only propagate here, and then once this change goes here, it will not be influenced by here. But in practice, this thing and this thing don't switch off instantaneously. Even if the clock signal is instantaneous, there's going to be some finite delay at which this will disable and this will enable. So there's going to be some finite, very small transparency window where any change in D can appear in Q. Okay. So in theory, the age-triggered flip-flop supposed to have a transparency window exactly at the clock age, the positive clock age of the clock. In practice, because the latches have a finite response time, there may be a possibility that this latch is not yet disabled when this latch is enabled. So the value races through here. Or for example, this latch is going to be disabled and this latch is going to be enabled. So before this latch can disable, this latch enable already, so it goes through here. Okay. So if you're saying from this latch is going to disable, this latch is going to enable, that is called the that is called the setup time. Okay. This data must be held constant sometime before the clock age, right? Because at the clock age, this one will enable, this one will disable. So the setup time means you have to hold this constant before the clock age when these things transition, right? When this one starts to enable and this one starts to disable, right? Because if you don't respect the setup time, okay, there's a possibility that this D value will update Q directly. Okay, so it means that the input of the D flip-flop needs to be stable, needs to be fixed, needs to be unchanging. The value has to arrive not at the clock age, but some small amount of time before the clock age. Otherwise, when this one is disabling and this one is enabling, there's going to be a small window of time where the D value can change Q directly. Okay, and if it's not really steady, is maybe the next value or a transition, you may get the wrong value to Q. That's what I mean. That's why we say the data must be ready here at D. Otherwise, it doesn't get propagated. Okay, and at the same time, after the clock age, there's something called the hold time. Okay, the hold time means after the clock age, you must still hold the D value constant for a certain period of time. Why? Because if you don't hold D value constant for a certain period of time, before this is totally disabled, any changes in D might actually corrupt this star, and this star has the rest of the positive clock cycle to corrupt Q. Okay, so what I'm actually explaining is using this concept of two latches, you understand that age-triggered flip-flops are not age-triggered exactly. There is a small window of time before the clock age, up to a small period of time after the clock age, during which if you make any changes in D, that change might actually end up corrupting Q. Okay. So the small period of time before the clock age is called the setup time, and the small period of time after the clock age is called the hold time. Okay. And why we mentioned this? We mentioned this because we talked about how fast does it take for you to actually compute your logic? When must your data arrive here? Previously, we said at the clock age, this output data is reaching here already, and you have one clock cycle before I reach here, right? But now I tell you about setup and hold time. It means you have less than one clock cycle. You have one clock cycle minus the setup time at which the data must reach here so that the flip-flop 2 can receive that value correctly. But hold on, wait a minute. Yeah, that's the setup time. Okay, so this is the worst case delay. The worst case delay actually is not the clock cycle, but the clock cycle time minus the setup time, because you have to arrive at least a setup time before the clock age. Okay, and you also have to include Even after the clock age, there is a finite propagation delay for the data from here to get to the queue. So the total time that fits one clock cycle is the propagation delay through one flip-flop, the propagation delay through the combinational logic, and the setup time. And that's expressed in this equation. Okay, so your clock duration must be greater than or equals to the time it takes from the output, the input here to propagate to the output here. There is a finite time, right, for things to update. The time it takes to cross this combinational logic, and that is what you are learning in logical effort in VLSI. You calculate the delay and the setup time of this flip-flop. Those three is the minimum clock duration. Minimum clock duration means maximum clock frequency. That is the fastest you can clock this design. Okay?
Okay.
Okay. It takes a little while to let this sink, but this is called the max delay constraint. Max delay constraint sets the frequency, the maximum operating frequency of your circuit. So in your critical path, it's not enough for you to identify your critical path. You need to identify your critical path, propagation delay of the flip-flop, and setup time of the flip-flop. Add that together, that is your max delay constraint. But as you studied in VLSI, max delay constraint is not just the critical path. There's the variability and all that you have to estimate. Okay, but the max delay is actually not just a combinational logic delay, it is the longest combination logic delay plus propagation delay through the flip-flop plus setup time of the flip-flop. Got it?
Got it.
Next, we talk about mean delay. Mean delay is a situation where when you clock this takes a propagation delay to go through here. It races through the combinational logic and it has arrived here even before the clock age has finished clocking. So it is possible for it to go through. Because you realize that I told you, right, that you have to hold this value here constant a whole time after the clock age. So if after the clock age, propagation delay plus the combination logic, if these two delay is faster than the whole time here, your output here is going to jump through two flip-flops, and this is called a race condition. And if the propagation delay through here and combination logic and through the propagation delay and combination logic is less than the whole time, you can actually jump 3 flip-flops. Okay, so this is called the mean delay constraint. Okay, so contamination delay is the shortest delay of the combinational logic, right? So it's the opposite of the critical path. Critical path, you're talking about the branch. Okay, and the reason why I say that is because the same logic stage, the same logic path, you realize from VLSI has multiple delays, right? Because it depends on which input is actually switching. Okay, so the fastest possible delay of that logic path is called the contamination delay. Okay, and that contamination delay plus the propagation delay of one flip-flop must be greater than the whole time of the flip-flop. Otherwise, you have what is called timing violations, race condition, which means that instead of your data jumping 1 clock cycle, then the next clock cycle jump here, your data jumps 2 flip-flops in 1 clock cycle or more than that, 3 flip-flops, 4 flip-flops in 1 clock cycle. It doesn't work, right? Because again, we mentioned that the whole point of synchronous state machine is every clock cycle there is one change, right? Because you're supposed to compute using the new data from the previous time cycle from the previous flip-flop, right? So these are violations of what we call the single clock synchronous discipline. That is 1 clock cycle, at every clock cycle age, the flip-flops are updated and the flip-flops take about 1 clock cycle to update here, and then at the next clock cycle, they go through the next flip-flop. If you have a situation where the data cannot arrive here in time, that is the max delay, or the data arrives too fast that it jumps 2 clocks or two flip-flops or 3 flip-flops, then your assumption behind state machine break down. the circuit will be in error, right? Logical errors, okay? Can you understand that, guys?
Sorry, Mister. Can you repeat again?
Okay, all right, I can repeat again. Okay, max delay constraint, you understand, right? Is
Yeah.
okay, this is the maximum clock frequency, it is setup time plus combinational logic time, and this is the critical path combinational logic plus the propagation delay must be equal or less than the clock period. Okay, the clock period, how fast you're clocking this. Mean delay constraint is the constraint that there has to be a minimum delay so that you don't jump 2 or more flip-flops in one clock cycle. Okay, and that is the propagation delay through this flip-flop plus the contamination delay, that is the shortest delay of this logic path, has to be greater than the hold time, which is hold time is the time that this data must be preserved after the clock transition. Okay, because if this changes after the clock transition, just after clock transition, if you change, you may actually jump 2 or more flip-flops. So what I'm just saying is that these max delay and mean delay constraint are just giving you the situations where in real life, if you don't control very carefully the delay through the combinational logic, you may end up breaking the assumption behind synchronous state machine. What is the assumption behind synchronous state machine? The assumption behind synchronous state machine is at every clock, the flip-flops are updated once at every clock edge. Boom, the clock comes, all the flip-flops are updated. Then it takes more or less one clock period for the combination logic to determine what should appear at the inputs of all the flip-flops. And then the next clock cycle, it gets updated. Okay. This is the synchronous state machine way of doing design. Okay. But in reality, if you don't control the delay, it is possible for the combinational logic to take too long to compute so that the value does not arrive at the flip-flop when it's supposed to arrive. So instead of updating the flip-flops correctly at the next stage, you update the old value in the flip-flop. So this is an error, okay? Error in your design, okay? It's not because you design error, but it's error because the combination logic is too slow. It cannot update the flip-flop when it's supposed to update, which is every clock cycle, the flip-flops have to update. The opposite also can happen, that is the combination logic is too fast that the flip-flop doesn't just update one flip-flops, like let's say here goes into this flip-flop, which might go into this flip-flop again. So this flip-flop, instead of just updating here, it will jump here and go here, boom, in one clock cycle. So your design actually has been corrupted, right? Because your assumption is that the combination logic is supposed to compute every new clock cycle, the updated output from the flip-flop, output from flip-flop will be computed by combination logic, and then it will present that new value, computed value, to the next flip-flop at the next clock cycle. Okay, this is how it's supposed to go. One clock cycle, new value of input coming in goes in the combination logic compute it. The next clock cycle, that combination logic ready to pass it to the next flip-flop. Okay, it's like one flip-flop, you jump. Okay, every clock cycle. But if you have a max delay violation, your computation actually does not reach the flip-flop on time. The flip-flop will pass the old value again to the next stage, and then that corrupts your design. Okay, your design doesn't work. Okay, or if it's a race condition, it will pass the value through 2 flip-flops or 3 flip-flops ahead of time. So it's the wrong value. Okay, Ken, do you understand what I'm saying?
Yeah, got it.
Okay. So now I'm tying back why this synchronous state machine, what is the assumption you're making when you're making a digital logic design? The assumption is that everything will calculate by the time of clock cycle. That's why you have to set the specification of clock cycle, because it really depends not just on your propagation delay of the critical path, it depends on your contamination delay, which is the shortest delay of your combination logic, and it depends on the setup and hold time of your flip-flop. You got it?
Yeah. So meaning that, Doctor, for the maximum delay, we pass over the O value, right? Is it right?
No, maximum delay, it doesn't even arrive on time. So the
Oh,
O
yes,
value is repeatedly passed. So let's say you need to pass, this is A, let's say this is B. B needs to come here after the first clock cycle. After the second clock cycle, B needs to come here. Okay? Let's say this is A here. First clock cycle, A goes here. So it's supposed to be clock cycle 1, A goes here. B goes here, B comes here. Clock cycle 2, B goes here. So it's supposed to be A, then B.
Yeah.
Max delay, if you violate, you have A go here, sorry, B go here, A go here. By the time next clock cycle, B has not arrived here. So the second clock cycle, you get A. So what happens is you get A here, you get A here again after 2 consecutive clock cycle. That's wrong. Okay? Mean delay is like you're supposed to get B here, A here, then the next cycle you get B. So you're supposed to see A, then you're supposed to see B, right? Yeah. But mean delay, in the clock cycle, you see A, so within one clock cycle, you're supposed to see A, then the next clock cycle you see B. But in one clock cycle, you see A, then suddenly the A becomes B. Okay, that's mean delay constraint. So in actual fact, your circuit output here never sees A. It has missed A altogether. It just sees B only. That's mean delay constraint. Okay, your circuit for proper operation, you're supposed to see A after one clock cycle. Then the next clock cycle, you see B. But what happens in mean delay is that first clock cycle, you see A, suddenly the A becomes B. So effectively, your circuit only sees B, never sees A. It sees B in the first clock cycle when it's supposed to see A. And that's it.
Okay, got it.
Got it?
Yeah.
Okay. So these are the two main constraints for timing. And for max delay, you need to take the longest propagation delay, which is called the critical path. For mean delay, you need to look at the shortest contamination delay. Okay? And it's not for the same path. You have to find the path with the shortest delay, and then the shortest delay of that path itself. Okay, that's the contamination delay. And then the critical path is the path with the longest delay and the longest delay of that particular path. Okay?
All right.
Okay, this is very important because I'm going to confuse you even more. This is called clock skew. Why you have clock skew? You're assuming that the clock edge is going to arrive at every flip-flop at exactly the same time. But you have forgotten to take into account that you actually have real physical wires with real physical capacitance that you need to charge. So it is possible that one flip-flop at the end of this chip and the other flip-flop at the end of this chip, the clock edge will arrive first here and will arrive slightly later here. So remember, the other assumption of your synchronous state machine is you're assuming that the clock edge is your synchronizing point. But what happens if the flip-flops see the clock edge at a different time? So they're synchronizing not at the same time. It's synchronizing at a different time. This is called clock skew. Do you understand where clock skew comes from? It comes from the fact that, okay, let's say you have okay, I didn't have a clock skew diagram for you guys lah. But basically, it's this idea that you have one wire that is connecting, that is driving the clock, right? And the clock is going to the millions of flip-flops in your design. But that clock is being carried by a wire. Okay, different clock flip-flop will be at different location on your chip. So the wire length will be different. So the propagation delay from the clock signal to that particular flip-flop clock input is going to be slightly different, right? So the example will be something like this. Let's say I'm going to tell you, I'm going to shout every 1 second, I'm going to say, ah, 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 ah. Okay, I'm just going to do that, right? And I'm asking you, Is, and you, Alvin, to synchronize. Every time I shout ah, you're going to click the mouse button once, and then the computer is going to record it, right? Are you, Is, and Alvin, are you exactly going to hear the ah at the same time? Exactly at the same time? Let's say you were sitting next to each other. Do you think you will hear the ah at the same time? At the exact same moment? Yes or no? Okay, Alvin says no. Is, you think yes or no?
I think Yes.
You think yes lah. If you're sitting together, yes lah. But now let's say one
Yeah.
of you is in Malaysia and one of you is in US. Will you hear it at the same time? I'm in Malaysia.
No.
Will you hear it at the same time? No, right? Okay, so
No.
you're not so far apart now lah, but I think you can appreciate now that the internet probably doesn't pass through the same path to get to both of you lah. So there's going to be a slight differential delay in when you arrive, right? But the R is supposed to synchronize your mouse click. Correct? So the R that I'm giving you is the clock edge. So you are all flip-flops. You're supposed to update your value. So you can see, because there's a slightly different amount of delay in which my clock edge arrives to you and to Alvin, you will update the flip-flop value at different time. And that has the effect that effectively, like for example, if I flip-flop 1 and flip-flop 2, if the clock edge arrive first in flip-flop 1 and the clock edge arrive later in flip-flop 2, it would seem as if you have a slightly longer clock period. Why? Because if the clock edge arrives exactly, you have 1 nanosecond, for instance, to complete all of this. But if the clock edge arrives in flip-flop 2 by 1 picosecond later, you effectively have 1 nanosecond plus 1 picosecond before you need to update flip-flop 2. Correct? So if flip-flop 2 clock is slightly skewed later than flip-flop 1, you effectively have a longer time window for this combinational logic. But if the opposite happens, if flip-flop 2, the clock arrives first, and flip-flop 1, you have a shorter time window to meet the contamination, to meet the propagation, the max delay constraint. Okay? Right? So now you can see, right? It extends and it contracts, right? So one case will be worse for max delay, one case will be worse for mean delay. Right? So the presence of clock skew, that is different arrival time of the clock edge, is going to slightly mess up your timing specification. Ken?
Yeah.
Okay. And this is just the equation lah, because normally what they'll tell you is that that's why when you talk about digital circuit design, the clock layout is very important, because they have to do their best to ensure that every single clock line have more or less the same delay to minimize clock skew. And it gets harder and harder as the chips become bigger. Okay, but your chips are not becoming bigger, your chips are maintaining the same size, but the transistors are getting smaller. So effectively your chips are becoming bigger lah, right? Do you understand what I'm saying? Is either if I have a lot of houses, okay, if I have a lot of houses, okay, and I'm building more and more houses, okay, so the distance that I need to walk for other houses is further, right? But if I maintain the same area and build the houses, but I shrink myself, my distance is also further, right?
Yeah.
Okay, so as we are cramming more and more transistors and the transistors getting smaller, the propagation delay, the differences in clock wire length can actually become longer. So clock skew becomes an important and is a bit of a worrying problem. So clock skew also influences. Now I'm going to throw one more thing at you so that your view of the world is realistic and perfect. And you understand why digital design is so tough, that you have to watch out for all of these things, practical effects. Your clock signal does not give you a fixed, they say you said 1 gigahertz, doesn't give you a 1 gigahertz clock period. If you actually turn on a logic analyzer or an oscilloscope and you put it on an oscillator, even a 1 megahertz oscillator, you will find that you will not get exactly perfect 1 microsecond clock duration. The oscillator will have a slight what we call jitter. That is, maybe at this particular time, this particular instance, it will have for a 1 megahertz oscillator, for instance, it will have maybe a 0.99999 microsecond. Then the next clock period will be 1.01 microsecond. Then the next clock period will be 1.005 microsecond. So there'll be slight variations in the clock period due to the non-ideality of the oscillator. Okay, and that can change with temperature and all that, because you've learned about the variability and all that, right? So jitter also can eat into your margin. So in conclusion, for timing specification, you need to consider the max delay constraint, flip-flop setup time, mean delay constraint, flip-flop hold time, clock skew, clock jitter, variability. Then you have a robust design. For the purpose of ADSD and VLSI, we are not going to consider clock skew. We are not going to consider clock jitter. Enough for you to consider max delay, mean delay, and variability. Enough. But when you go into the real world, don't be katak bawah tempurung. You need to understand clock skew and jitter also affect your timing and the robustness of your design. Okay, what happens if you ignore all of this? Well, if you're lucky and if your circuit is not really pushing the cutting edge of speed or complexity and your process technology is great, your specs are not so high, you'll get by, the design will going to work. But this all matters for high performance digital circuits where you're trying to squeeze every last drop of performance, where the difference between that last drop of performance will be whether you can charge more or you can outsell your competitor, and whether your product is going to be robust and what is the yield. Okay, Ken?
All right.
Okay, can you go on a little bit more?
Yeah, sure.
I want to give you one more thing, which is I want to cover this idea of metastability. Okay, why we want to cover metastability? What I told you is that the flip-flop, okay, if for example you didn't obey the setup and hold time, the D value can actually leak into the Q value. Either it can rush through in the case of mean delay, or it actually doesn't actually go through in the case of max delay. Okay. But what I have not told you is there's even a worst case scenario where if, for example, this happens somewhere when the input signal is transitioning, you may actually get at the output of your flip-flop not a logic 1. You won't get a logic 1, you won't get a logic 0. You'll get the metastable value, which is the voltage in the middle of the two. And then you're in trouble. Okay. What is metastable? You have learned all this while that digital circuit has a logic 1 and a logic 0. Logic 1, logic 0, logic 1, logic 0. Logic 1 is VDD, logic 0 is ground, all that kind of stuff, right? But there is a particular circuit configuration in this positive feedback, where you have two inverters in a feedback structure like that, where the circuit can actually hold a third stable point, which is the voltage exactly in the middle between the VDD and the ground. Not exactly in the middle, but somewhere there. When will be the case when it's not exactly in the middle? When your PMOS and NMOS transistors are not designed for equal resistance. Because we went through, right, the inverter, when your PMOS has to be roughly twice the size, NMOS is the NMOS then is roughly that same speed. But then again, the mobility is not exactly twice. The mobility of holes is not exactly half the mobility of NMOS. It's approximately half. So you're not going to have a perfectly symmetric inverter. So it's going to be somewhere in the middle. Okay. So there is this hypothetical point, and it's not so hypothetical because it really happens in real world. And as you go through the statistics, you'll be horrified that it actually happens more frequently than you think, where the circuit can actually hold the metastable point. And why is that a bad thing? Because if it holds a metastable point, it's going to propagate the metastable point to all the circuits in the middle, and the metastable point is out of the noise margin, right? Because you studied in digital electronics that logic 1, there's a range. It's between VDD, then if it's like VDD 3.3 volts, it's like maybe 3.3 to like 2.7 volts, for instance. And then logic 0 is from ground, voltage 0 volts to something like 0.7 volts or something like that, right? But nothing is defined in between 0.7 to 2.7, right? Nothing is defined there, right? So if you land somewhere in between there, it's not logic 1, it's not logic 0. And now I'm telling you, the worst case, there are certain digital circuits that can actually hold that value. So when it holds that value, what happens? You propagate this intermediate point and you lose all your data going down the circuit. So that's why metastability is bad, right? Because your circuit suddenly stops becoming a digital circuit. It becomes a ternary circuit because it's a third state and there's no meaning attached to the third state. And the worst is you're going to wipe out all your calculations because the metastable state is going to propagate. Okay? Okay, now This is a clincher. What is that circuit structure that can actually be metastable? It is the flip-flop. Seriously, it is the flip-flop. Why? Because storage element, how do you actually have a storage element from gate? Use a feedback structure lah. If I put a logic 1 here, logic 0 is here, logic 0 here, logic 1 here. Okay. So if I cut out the logic 1 here, if I disturb the logic 1 here, okay, this output is going to actually restore the logic 1 here. Okay. If I disturb the logic 0 here, this input and this flip-flop is going to restore the logic 0 here. So the most basic memory element would be two inverters like that. So I can actually design a latch, something like this, right? I have one switch here and a one switch here, okay? If I want the latch to be transparent, I will turn on this switch, I turn off this switch. Then the value will go through this inverter, but it will not be fed back, okay? So this is how I make the latch transparent. Remember when I said, when you enable the latch, whatever is the input here will appear at the output. Yalah, here is inverted lah, because you can throw an inverter here, it's okay. So if I turn on this switch, I turn off this switch, my latch is transparent. If I turn off this switch, turn on this switch, I remember what's at the output lah, through this reinforcing circuit, this feedback circuit, and I'm no longer sensitive to the input. So these two switch to inverter structure gives you the basic concept of a latch. And just now you went through, two latches will give you a flip-flop, an edge-triggered flip-flop, okay? So, and now you have gone through the switching idea of switch logic. You know how to build inverters. Okay, you can just put two inverters here, and you know how to build switches, because switches is nothing else but a MOS gate, right? Either CMOS or PMOS, or you can actually have a PMOS or NMOS, or you can actually have both PMOS and MOS. They call a CMOS switch. Okay, so you know how to build the very simple latch. But if you build a latch based on this, it's going to be a pretty crappy latch, lah. That's not the exact way latches are designed. There are more complicated, many different variants of latches, which in the older digital systems, they will give you recipes for that. But nowadays, they just give you the standard cell library. But for the purpose of understanding where does metastability come, metastability is that third logic point, is not binary, it's ternary, that third point which you hope doesn't exist, but it exists because of this memory condition, this internal positive feedback that retains memory. Because if you look at these two inverter configuration, you actually have a transfer curve like that lah. That is the input here will give output here lah. Of course, because input here, if at the input here, the output here, right, is two inverters means it's a buffer, right? So input here, if it's logic 0, will be logic 0, logic 0, logic 0. Then if it's logic 1 here, it will give logic 1. And then there is this kind of funny situation here where if you are somewhere in this case, these two inverters actually function like an amplifier. Okay, so the amplifier, when you have this value here, it will give some value that is close to VDD. Okay, when you have some input value here, it will give you some value that's close to VDD. Then at this input, you become close to VDD. Then you'll be even close to VDD, then it will positively use positive feedback. You rapidly go towards VDD. Okay, so this kind of memory storage, this kind of structure, this basic regenerative positive feedback structure has two things. One is it allows you to remember because it has a kind of very rapid positive feedback. Is that if you have a value that is very close to logic 1 here, the positive feedback will rapidly drive it to logic 1. If your value very close to logic 0, the positive feedback will drive it very quickly to logic 0, and it remembers that way. But the side effect of that is exactly at the middle, there is a unstable point. Okay, that is a metastable point. Why is it called metastable? It's called metastable because it can theoretically hold that value for a very long time. Okay. But because of thermal noise and maybe interference, if you tip the voltage slightly away towards VDD, the positive feedback will rapidly force it towards VDD. Or if you tip it slightly towards ground, the positive feedback will rapidly tip it towards logic 0. So metastable will not last long in your system, but it can appear in your system. Okay. And it appears because of the positive feedback memory element, which is latches. Okay. So this is the important part lah, that if, for instance, you happen to open the latch when the input is transitioning. Okay, I'm now telling you where the metastability can happen. That is, if you make the latch, if you happen to turn this off and turn this off, turn this off and turn this on when the input here is changing, this thing can go to metastable. This is why you also, the second reason why you also need to have a setup time, because these switches are turn on and turn off at the clock edge. So when you turn off and turn on this, the input must not be changing, because if the input is changing and you actually end up turning this off and turning this on when you are at the metastable point, this will store the third metastable state and your logic will be corrupted. Okay, so this is why you need to have set up the whole time. You need to have a transparency window. You need to have a slight delay before the clock edge and a slight delay after the clock edge. You cannot change the input. The transparency window is a finite time duration around the clock edge. The first reason is because you don't want to unnecessarily have the input corrupt the output due to race conditions or things like that. The second is you don't want to unintentionally force the system into metastability, because if your input happens to be transitioning at the clock edge, you may throw your flip-flop into metastable state. Okay. So this is the proof of metastability. This is actually from Professor Deli's lectures. It's showing 1, 0, 1 on the oscilloscope. So 1 and 0, right? This is showing you over multiple repeats. You look, there's metastable here. This is metastable state. This is the logic voltage in between logic 1 and logic 0. Okay, and you see that the metastable state, sometimes it resolves very quickly to logic 1, sometimes it recalls very quickly to logic 0, and sometimes it takes a long time to resolve there. But you find that generally it tends to resolve within some finite period of time. No, it does not stay forever in the metastable state. Why? Because that's why it's called a metastable state, because a small amount of noise that can tilt it slightly to logic 1, the regenerative feedback, the positive feedback of the latch will actually ramp it up quickly to logic 1, and a small amount of feedback or noise that can tilt it towards logic 0 will ramp it very rapidly to logic 0. Okay, so yeah, so metastable state. And here, if you're interested, the Delhi book actually has some calculation to tell you how frequently, what is the probability of you entering a metastable state. So there are two situations where, in general, where in digital logic, you can actually enter metastable state. One is if you're changing your inputs around the clock edge. That's why once you meet the setup and hold time,
Hello.
I hear your voice, Alvin.
I think something went wrong.
Yeah, I guess so.
Uh,
Hi guys, can you hear me?
Yep.
Yep.
Sorry, I got booted out again. I think, I don't know why today my connection is so bad. Okay, I'm just concluding lah. I'm just saying, if you're interested, you can calculate the probability. I think that there are two situations where metastability can occur. One is if you actually change your inputs at the clock transition lah. So if you observe the setup and hold time requirement, which you must in all digital design, you will not be able to induce metastability. The other situation where you can actually have metastability is when you are sending inputs between different clock domains. And that will be the example. Let's say you're connecting maybe computer 1 to computer 2 or microprocessor 1 to microprocessor 2. If they're not sharing the same real exact same clock, you can actually get into metastable because in clock 1, I'm actually just changing the clocks at that time. But what happens if the clocks are exactly 180 degrees out of phase, or they're slightly changed in such a way that the output is, if they are just out of phase by setup time or something like that, right? So that's where if you're receiving digital inputs that are not aligned to your clock age, that's when metastability can happen. So when you are actually interfacing between two synchronous circuits that do not share the same clock or do not share the same clock frequency, if they are a different frequency, or even if they are the same frequency but different clock, and the clock ages not necessarily are at the same phase, let me say align, metastability can happen. And in that case, usually what happens is, what you do is, the key result here is you throw a flip-flop in between. Okay, if it's 1 bit, you throw a flip-flop in between. Why? Because if metastability happens, the best way to recover from metastability is to wait. Okay, so when the flip-flop, the reason you have flip-flop is it takes some amount of time for this metastability to recover, then this flip-flop will shield this logic circuit from this metastability because you are giving it 1 clock cycle to recover. If you have 2 flip-flops, 3 flip-flops here, you give it 2 clock cycles to recover, and then you shield the circuit from propagating the metastable state. So if you have a single bit that is coming from a different clock domain, different clock domain meaning different clock with not same frequency, or different clock with same frequency, not same phase, to prevent metastability, you add flip-flops. And adding flip-flops, the idea is just you wait long enough and you isolate the digital circuit from any metastability that may happen, right? Because this flip-flop is clocking this signal A, and this signal is not aligned to this clock. So metastability can occur here. But of course, if you wait long enough, this flip-flop will resolve this metastability because of the positive feedback. And if 1 clock cycle is not enough, the metastability may be propagated here. You can have another flip-flop here, another flip-flop here. So you just build as many flip-flops as possible, okay, until you can wait long enough, the prerequisite number of clock cycles to wait for the metastability to resolve. The other approach to handling this, if you have multi-bit signal, that means you have a bus, 4-bit, 8-bit, 16-bit, is you throw in a 5-4. Okay, so 5-4 is very special because you write you write into the memory and you read from the memory. You can write at 1 clock frequency, you can read at a different clock frequency. Okay, that is why 5-4 is very special. Okay, so 2 solutions for you to overcome metastability. 1, if it's single bit signal, throw flip-flops in just to delay the signal long enough. 2nd, if it's multi-bit, you can use a 5-4. Okay, now I am not going to examine you on metastability, and I'm not going to examine you on metastability recovery for a digital system design. They said the goal of tonight is just for you to be able to understand max delay, mean delay, how to do timing specification. And timing specification for this course, only max delay, mean delay, and variability, you need to account for that. Clock skew, jitter, metastability, no need. But you need to understand metastability because this is the 2nd reason why we need to consider setup and hold time. And you also need to understand that when you're actually interfacing circuits between different clock domains, you need to ensure that you don't induce metastability in your circuit at the same time. So you throw in flip-flops to delay, or you throw in a 5-4. Okay?
Right.
Okay, that's all I have to share for tonight. Any questions, guys?
Nope, I have no question.
Nope, ah. Okay, so I hope it's valuable to you. I know maybe it might seem a lot lah because it's like kind of oh every week there's more and there's more and there's more. But yeah, I just try to keep pace. Not all of it is examinable. So you know the core is just that six modules lah, practical modules. Because if you can do that, you've met the requirement lah for this course, which is you know how to design. The rest are more for your own understanding. You can pick it up at your own pace after the course, as long as you know it's there, you know the reason why it's there, and if you actually encounter it in your workplace, you know where to look up for the resource. That's good enough. Okay. So if there are no more questions, I will close the session for ADSD tonight. And tomorrow night, I think 8:30 is okay again tomorrow night, or for VLSI, or you guys want a different time? We can do it earlier, we can do it slightly later. Also, maybe we go for 1 hour plus, or if it needs to take longer, then we'll go to 2 hours, 2.5 hours like today. Tomorrow, again, the focus will be on VLSI, Q&A. Any questions you have, any doubts you have, I can clarify. And if you have no doubts, then I'll just show you the optimal transistor sizing using logical effort lah, for delay path. That's not too difficult, it's quite straightforward.
I think 8:30 just fine for tomorrow.
8:30 just fine, is okay. I think Alvin also mentioned it was okay lah. So
Yeah.
okay, tomorrow after the optimal design of the width, I'm actually done with VLSI material. Maybe at most we have one more session. I just go through the whole work example to piece things together. But you've got your major assignment out plus all the other small assignments. VLSI, we're done already. After tomorrow, essentially, you know everything I want to teach you already. Okay. DSD, we still have a little bit more. I have to get out the modules for the interconnect, the scheduler, the FIFO. But the FIFO already I showed you is in the Chu book. Probably just use the same one. But I'll craft it in a way that you can see the instruction load store pattern. And it's just the pipeline one and the scheduler and the interconnect. Once that is out, DSD basically we are done already. Okay, you just have to finish up the assignments. So we are rapidly coming to the close of the course topics. So VLSI after tomorrow, pretty much you actually know enough already. Just have to master it, review it, and things like that, and then work on the assignments to really enhance your understanding. Okay.
Okay.
So I think we are sort of making good time. We can still end VLSI. Will probably be ending like again slightly before middle of August. And DSD maybe up to like 3rd week of August or something like that, 3rd to 4th week of August, which maybe is cutting it a little bit, but I think you guys can still make it on time. And as I mentioned, I'm available. Just let me know if you want to have a Q&A session. But I think beyond this, I will not have much. I will not have anything to present anymore, because really I think it seems to be quite a lot already for you to master. So it's no point to go more unless you want. If you want, then I can go on. It's up to you. Just let me know. VLSI, if you want, the additional thing will be we'll look at logical effort sizing with wires. ADSD, if you wanted more, what would we do? I have to think a bit more about ADSD. If you wanted more, if you wanted more, then maybe you can actually take the step to do static timing analysis using the tool, right? Because today actually what I've covered, the max delay, mean delay, setup time, hold time, this is under what we call static timing analysis. Okay, so I think previously in the example of the tool example where in VLSI, where I showed you there was a static timing analysis example. I want to bring that up again because now I can actually show you what it means. So just give me a second while I look it up. So is it under synthesis reports? Yes, that's right. How do I do this? I need to show my screen on my desktop. Okay. All right. So if you remember the Qflow Docker, there was an example where I did the synthesis as well as the layout. And then it is a video. Then in the synthesis, I was showing you there's the reports. So register to register max, this gives you the critical path delay between two flip-flops. Okay, so for this particular design, there are 4 paths. Okay, maximum delay paths, right? This is the max delay. There are 4 paths, and the name is this 18 clock to 9 delay. The max delay is 961.717 picosecond lah. And here they're actually telling you what is the particular transition and how much is the time lah. Okay, so they are and then they have an estimate of the clock skew, and they have the estimate at the setup time of the flip-flop. Okay, so rash to rash max is the max delay constraint. Rash to rash mean is the mean delay constraint. The contamination delay is given here. Okay, so static timing analysis, the Vesta tool here, but in commercial environment you have Cadence tool and all that. But when they say static timing analysis, they're actually looking at what is the max delay for your particular design, what is the mean delay for your particular design, given flip-flop setup hold time, propagation critical path delay, as well as contamination delay. Okay, so it's here. So they give you 4 types of information. The max delay, which is between registers are flip-flops, the flip-flops. The mean delay between registers, the pin to register delay, that means from the chip pin, that means the input, some input from a different clock domain or anything, to the arrival time at your first flip-flop, and the pin to register minimum delay. Why? Because this one's special a bit. Those pins, as I mentioned in the introductory video, they actually have a big pad, big capacitance, so there may be a slight different delay, different rise time, different fall time, so you might care about that. But I just wanted to highlight what we covered today is the essence of static timing analysis. So when people say static timing analysis, don't get shocked. You already know what that means. That means the max delay, mean delay between two flip-flops. And the static timing analysis tool gives you all the major paths and the main delays. So again, when I told you about in the variability section, you have to consider a bunch of the near critical path delay. Well, the tool already gives you the near critical path delay. All these are the near critical path delays. Okay, so let's say in the exam or something, if you need to calculate this, if you play around the tool and you can synthesize your design, you can just report to me the static timing analysis results. Okay, and you can say this is what I've synthesized, and this is more realistic because it includes the wire delays as well. Okay, whereas if you were to actually hand estimate by the circuit, you are not including wire delays, you're only including the gate delays, but that's still okay. I accept that either, because both ways will have pros and cons. If you use the tools, this will be more realistic like industry, but you have to go in and find the mapping after synthesis. What does this mean? What budget? So I'm actually forcing you to go and sketch out the actual implementation after synthesis. Okay. Whereas, so you will take more time in sketching that out and identifying what is that path, what is the logic in that path. You have to show me the logic in that path. Whereas if you do it by hand, you actually have to take more time to calculate it, but you already know your design by hand. Okay. So both approach totally acceptable in exam. Okay, and if you come up with a third approach that is innovative, that is correct, that's all that accepted, as long as you give me the correct answer. Okay, so the exam questions and any other assignment questions are open-ended. If you have your own novel way, this is also encouraged, but it must be correct. But of course, you don't have to invent your own way. You can also use the way that is taught in class. And there are at least 2 ways for you to do this analysis. 1, 2 ways. You convert the Verilog, you synthesize it, you place and route it, do the static timing analysis with the tool. B, you actually design by hand. You design the logic and all that kind of stuff. You estimate using the logical effort method. Okay?
Okay.
Okay, guys. Okay. All right. So I hope it's been a helpful session. So if there are any more final questions I can take, that would be good. I can take it now. Otherwise, we'll call it a night, and I'll be with you tomorrow again at 8:30 for VLSI.
Okay.
No questions?